My name is Simon de Montigny. I will be presenting the paper Adapting Ensemble Neural Networks to Clinical Prediction in High-Dimensional Settings, which was the focus of my postdoctoral internship under the supervision of Philippe Broët at the Sainte-Justine Research Center in Montreal. The study of neural networks in the context of clinical data, in particular survival data, goes back to the 90s. The first propositions of survival neural networks were lacking methodological rigor. Recently, many deep learning models have been proposed for survival data using regularization and validation methods. Yet, two limitations remain for clinical applications. First, the loss functions of these models, based on likelihood, do not measure predictive accuracy. It is common for models to have different performance in ordering pairs of patients by their survival probability, but to have similar performance for the accuracy of survival prediction per patient. Second, clinical data is often of the fat data type. That is, the data matrix has a much larger number P of possible predictors than the size N of the patient cohort, but with only a small number of relevant predictors. To improve neural networks for clinical applications, we thus propose a new survival learning algorithm based on ensembles of neural networks that minimize the integrated Brier score, a sound metric to evaluate the performance of predictive models. To achieve this, we link the neural network to a semi-parametric survival model. Furthermore, we optionally use L1 penalization to improve predictive accuracy in the context of fat data. We consider an improper semi-parametric survival model, which includes a long-term risk function phi and a short-term risk function psi that will be represented by the outputs of a neural network. The function S of t represents the probability that the patient having the vector of covariate z will survive longer than time t. We say that this is an improper model because there is a fraction of patients that will not incur the health event of interest, that is, non-susceptible patients. That fraction, also called the tailed effect, is determined in the model's expression by having the function a of t reach 0 at the time of the last uncensored event of the patient cohort. The long-term risk function phi controls the tailed effect. As for the short-term risk function psi, it affects the survival distribution of patients that will incur the health event, that is, susceptible patients. Having an explicit survival model, we can use the integrated Brier score as a loss function. The integrated Brier score is simply the integral of the Brier score, which is computed based on the estimated survival of all patients of the cohort over time t. Patients that already incurred the health event of interest by time t have a survival target of 0, and the patients that are still followed at time t have a survival target of 1. Note that if patient I is censored at time t, the corresponding term of the summation in the Brier score function is equal to 0. To account for censored patients, the error between the survival target and the estimated survival is inversely weighted by the estimate of the censoring distribution. The estimators used in constructing the survival model are naturally defined as piecewise functions that assume a constant value between two successive events. Thus, the expressions for the integrated Brier score and for the Brier score can be simplified as shown here. The coefficients C are adjusted to account for the inverse weight for the length of time between two successive events and for the null terms due to censoring. To represent the long and short-term risk functions, we propose a three-layered feed-forward neural network as the basic unit of the ensemble. The loss function of the network is based on the survival model and the integrated Brier score which we have presented. As shown on the right, we implement L1 penalization with an additional layer which multiplies each input by a weight that is initialized randomly around the value 1. These additional weights are used to define the penalty term. We implemented the neural network in Python using the Keras library. For a patient I, the risk functions generate the survival model, which must then be evaluated for every Brier score piece. To adapt the neural network to this particular computation, we duplicated the model's outputs and used a list of custom loss functions, each one serving as a placeholder for the target and coefficient of a given Brier score piece. The first table, down left, represents the target data for patient I. Each line of the table corresponds to the parameters required to compute one Brier score piece. The second table, down right, represents the corresponding neural network outputs, which are actually identical for every line. The code snippet illustrates how the lines from each table are combined across the whole cohort. To evaluate the total loss of the network, the custom loss functions are all added together. We tested the proposed survival neural network ensemble on 3 versions of the PBC dataset. The first version consists of the original dataset with 17 predictors. The second version adds 500 uninformative variables, and the third version adds 5,000 uninformative variables. We compared the survival neural network ensemble with no penalization and with penalization to a random survival forest and to a baseline ensemble of linear units. We trained the bootstrapped neural networks and the bootstrapped baseline models in Keras using the Adam optimizer. The resulting survival estimates are then averaged over all bootstrapped models inside the ensemble. The training setup is described in more detail in the paper. The random survival forest was trained using standard methods from the random forest SRC package. Our results show that the survival neural network ensemble with penalization provides the lowest out-of-bag integrated Brier score. It is also robust against the increase in uninformative variables compared to the other model. To illustrate how predictions differ from one model to another, we can plot out-of-bag survival curves for groups of high risk, medium risk, and low risk defined with regard to the survival probability value at the time of the last uncensored event. High risk is defined as the lower quartile, medium risk is defined as the 2 central quartiles, and finally low risk is defined as the upper quartile. We see, for example, with p equals 517, that the penalized survival neural network ensemble shows a greater separation between risk groups than the random survival forest. Thus, the neural network ensemble is more optimistic for the low-risk group and more pessimistic for the high-risk group. To conclude, we have shown that the proposed neural network ensemble strategy can provide better predictive performance than survival random forests on the PBC dataset. The originality of the proposed model lies in its choice of loss function to train a neural network ensemble with regularization. Future work will evaluate the interest of such an approach in ultra-high dimensional genomic datasets.